do this. And hello everybody who's watching on the internet, and welcome everyone who's in here in real life. So let me zip along to where we're supposed to be. So first of all, I hope you all kind of remember the stuff that we were talking about last. It's complicated. Remember, the last lecture was pretty complicated. Did anybody find it complex? Hard to understand? No? All right. Yes? Kind of people seem. I'm just trying to get you to respond a little bit. That's all. But anyway, I just hope that you remember that as you go up into the atmosphere, because remember we're doing circulation of the atmosphere, as you go up into the atmosphere, the pressure goes down, right? So it goes down. So that means that if you are a parcel of air and you start rising through the atmosphere, you are going to feel a decrease in pressure, right? So you're going to depressurize. So what's going to happen to you? You're going to expand, right? So if you're a parcel of air and you're starting off near the bottom, you're going to start rising. You'll expand, okay? And then if you expand and you depressurize, remember this whole thing, right? You depressurize, this thing gets very cold, right? So you all know you can, even if you spray this for too long, it even gets frost on it, right? So decompresses. You get colder as you decompress. That's called adiabatic cooling. Adiabatic cooling. So make sure you know that term, because on the final exam, now the next test, right? The last test, the final exam. So the final exam, if I refer to adiabatic cooling, you got to know what I'm talking about, right? So there's adiabatic cooling. That's cooling due to depressurization. Okay, so then that causes the cooling, and then you cool until you hit the special temperature at which you start condensation, which is called, what's the pressure at which you start to condense out water? Dew point? Yeah, the dew point. Okay, so you start going and going, cooling until you hit the dew point, right? And then you start to condense out water. So at that point, there's a change in the lapse rate, okay? What is the lapse rate again? Does anybody remember what lapse rate is? Lapse rate? Yeah, it's the rate of temperature change with altitude, right? So there's a change in the lapse rate. Why does that change in the lapse rate occur once condensation starts? So it cools down. Things aren't getting cold as fast when this condensation starts, and why is that? There's some heating process that is offsetting the adiabatic cooling. Yeah, latent heat of condensation, okay? So once you start condensing it slows down the lapse rate, okay? So anyway, when you hit the dew point, you start doing condensation. Once all the little droplets of water condense together and they combine together and get larger, they can finally start to get precipitation. So that's how you get weather, and you get all the storms and rain and all that kind of exciting stuff, okay? So there's the dew point, talked about that, and how hot air rises. And so anyway, I think this is kind of where we left off, right? Around here. So we should talk about this. So number 6, so we're on lecture assignment number 16, and I think we're on number 17, right? So we were kind of getting to this point. I was trying to explain that what makes the weather and the rain and the storms and things like that. Well, you got to get the air to rise so it can cool, right? You got to get it to rise so it can cool. And I realized also I should probably take roll. I've got to do that. So let me do that really quick. No Clarissa. We have Samantha, both Samanthas are here, and Eliana and Francis and Hayden and Gavin and Amanda. No Alex Cox, but there's Alex Trevino, Bree, there's Valerie, Kayla's here, Julia Garcia's here, with the necklaces and the C and her name. And then, that really helped, thank you. That's what I needed. I just needed I don't know what you call that, like a mnemonic device. All right, and then Tim's not here. He doesn't really show up too much anymore. Jaden is here, and Colton, and Steve, and Gus, and Kai is here, and Liam's here, and Natalia's not here. So sorry for that interruption. All right, so we want that air to rise. Now, how do you get air to rise? Heat, right? So it's like a hot air balloon effect, right? So you want it to become hot so that when the air rises, if it's relatively hot compared to the surrounding air, it'll start to rise like a hot air balloon, because hot air is less dense than cold air, right? So it rises due to buoyancy effects, okay? So you can imagine if there's a particular hot, just like in a room, there's a hot place in a room, like a radiator, it's going to make the hot air rise, it's going to rise up, it's eventually going to cool, it's going to sink, and it's going to circulate, right? So these atmospheric circulation, right, that's what we're studying today, and we have been studying, right? Atmospheric circulation is going to create these convective currents. You get hot air rising, it's going to cool off, it's going to get cold, and it's going to cool, okay? Now, so this is what happens, actually, is that the warm air rises, and as it rises, it'll start to cool adiabatically, right? And then it'll eventually start to sink. And actually, by the way, the opposite can happen. You can have, not only can you have adiabatic cooling, you can have adiabatic heating as well. So as air sinks, it will actually heat up due to compression, okay? So it happens perfectly in reverse too. You get adiabatic cooling when it rises and depressurizes. You get adiabatic heating when it compresses and goes to a higher pressure. Okay. So what is a common process that can make air rise? Is there anything you can just think of off the top of your head that might make air rise? Because that's the whole thing. We want to make the air rise. So what are some things you could think of that might make air lift up and rise up? So that would be like convection. So there's convective currents, right, that can make it rise. So there's, for example, there's actually a huge convective cell over Earth, right? Because hot air rises in the center, right near the equator, okay, and it's going to cool and sink near actually the tropics. So there's actually these huge convective cells that go on called the Hadley cells. We're gonna talk about those in a bit. There are other things though that can cause temperature, can cause things to rise too. So anyway, so convection can cause air to rise, and we're going to get convection by the way the sun heats up different surfaces, right? So, sorry, am I talking to? Right? Oh yeah, the sun. Yeah, the sun. Sure, the sun. Okay, sorry. Okay, so all right. So how does the sun warm up the Earth's surface? So number 18 is asking, how does the sun warm up the Earth's surface? And there are a few ways to transfer heat, right? You've probably heard of some of these things. There's convection, there's conduction, and there's radiation. So the way that the sun actually heats up Earth is radiation. And it has to be through radiation because it's the only way of transferring heat through outer space, right? Conduction and convection need to have some kind of material to transfer heat, but radiation does not. Radiation can actually transfer energy directly through empty space, outer space. Okay, so the sun transfers heat to Earth to create these convective cells on Earth through radiation. And what kind of radiation do we receive from Earth? What do you think of, by the way, when you hear that word radiation? What's that? Fallout? Yeah, because don't you usually think of like radioactive, like radiation, and like X-rays and like nuclear bombs and things like that? You think of radiation, right? And it's all part of, actually that radiation, it's all part of the electromagnetic spectrum and the whole spectrum of radiation. So there's the dangerous kinds of radiation. There are dangerous kinds of radiation over here like X-rays. And there's slightly less dangerous versions of radiation, things like ultraviolet, right? Ultraviolet can be a little bit hazardous too. You can get skin cancer and things like that from ultraviolet light. And that's all types of radiation. So ultraviolet light is a type of radiation. The light that you can see with your eyes is a type of radiation. And there's other things that, you probably heard of infrared, right? Have you ever heard of infrared radiation? So infrared is another kind of radiation. And sometimes you can get infrared light that is so infrared you can't see it. It's kind of the flipped opposite of ultraviolet, okay? So there's infrared radiation, you can't see it, right? It's there, it's energy, it's radiation, but you can't see it. And then there are other things. There's other kinds of radiation. Microwaves inside your microwave oven that you use to pop popcorn or heat up tea, that's radiation. You're literally using, I know it's kind of weird to think about that, but when you're popping popcorn or whatever in your microwave, it's literally just using like a very bright light that you can't see to heat up your food. That's what all a microwave is. It's a type of radiation. Same thing with TV waves and radio waves and AM. You've probably heard of AM and FM radio, right? Those are all types of radiation. They're just types of light, but it's all the light that you can't see. The world is filled with all this light you can't see. You only see, right, a very narrow band of the radiation that is actually available and emitted by the sun. So you're only seeing with your eyes a little bit of the radiation that's put off by the sun. You only really see about maybe 40% of what the sun puts out. And the rest of it is, infrared, microwave. Isn't that weird to think that the sun emits microwaves? It does. It even emits radio waves. So the sun even emits AM radio waves and FM radio waves and TV waves. It's kind of weird, but it does. And it also emits, of course, ultraviolet, and also emits some other stuff like cosmic waves and X-rays and things like that. So all those different kinds of waves are absorbed by Earth's atmosphere and absorbed by the land surface, and it causes different levels of heating. Okay. So what are some things? So how does the sun warm up the surface of the Earth? It does it by radiation. Right, and some of that radiation, only about 50% of it is absorbed at the surface. And the rest of it is maybe reflected out by the atmosphere, reflected out by clouds and things like that. Some of it is absorbed, quite a bit of it, 19% of that radiation from the sun is just absorbed by the atmosphere and absorbed by the clouds. Okay. So I've showed you this one a lot, right? So what are some things that cause differences in temperature at the surface, right? Because that's kind of what we're going for. We're looking for why some air might be hot and causes it to rise, and some air might be relatively cooler, right? So you know that over the land, things heat up faster, right? We've talked about this a few times in this class now, so I'm not going to go over every little detail of this, but remember that things over the land, the air will heat up faster over the land because the land gets hotter faster, it heats up faster during the day, and that can cause it to rise and to convect. Okay. Cause the air to rise, I mean. Okay. Now, what are some other things that affect how much the different parts of the Earth are heated? Well, another thing obvious is latitude, right? So the equator, very close to the equator, it's hotter. As you go near the poles, it gets progressively cooler, right? So that's another thing. So different kinds of land surfaces. I'm looking at number 19 right now. Okay. So different kinds of land surface, whether it's land surface or water, that can affect the land type. That can affect how much the land heats up. The latitude can affect how much the land heats up. What are some other things that could affect kind of like average temperatures in a particular location? Like if you wanted to figure out like how hot or how cold a particular place is on Earth, what are some things you would consider? You might consider whether it's, land or coastal. You might consider what the latitude is. What are some other things that can affect it though too? What's that?
Whether a place has plant life or not.
Oh, sure, yeah, and that actually goes into something called albedo. That's how much energy from the sun is actually absorbed by the surface versus reflected out. So plants can actually decrease the albedo so they absorb more heat energy from the sun. So that can do it. Think about this. Think about something, a place like Colorado has very high elevation. Do you think elevation can affect surface temperatures as well? So that can affect it as well, right? Elevation plays a role as well. So those are just a few things. The albedo, that's how much light is reflected by the land surface. The elevation, the latitude, those are all things that can go into how Earth receives different amounts of heat over its surface and how much it heats up, and therefore how much convection occurs and how much air rises up, and it goes into all that. Okay. All right, so here's a question for you. It says, why are temperatures, number 20, it says, why are temperatures normally lower at high latitudes? Okay, so we're going to kind of get into that. So why are temperatures normally lower at high latitudes? And so by that I mean like near the poles, right? The poles you have higher latitudes. Okay. So a lot of people think this is accidentally, mistakenly. They think it's because when you're at the equator, you're kind of like you're closer to the sun than maybe if you're like up here at the North Pole. And you see what I mean? So a lot of people will think that. And I even one time I caught my wife, we homeschool our children. One time I caught my wife trying to teach my children that. And I walked in, I was like, no! So that, I mean, it's true. You are like maybe a little bit closer to the equator, or a little bit closer to the sun if you're at the equator. But you have to remember that you're maybe like 100 kilometers closer, and the sun is like 150 million kilometers away. So it's not really that big of a deal, that you're that much closer. So the actual reason is that the light coming in at the equator it's like hitting the Earth straight on, right? So the light coming from the sun hitting at the equator is hitting dead straight on. You see that? Whereas the light that comes in at like the poles or at high latitudes, it's at an angle. And so that light energy, if you imagine, this is maybe a good way to picture it. Imagine shining a beam of light directly straight down. The energy of that light is spread over a smaller area than if you put it at an angle. If you put it at an angle, the light is spread over a larger angle. Do you all see that? Or sorry, a larger area. So do you see how like the same amount of energy is spread over that area versus the same amount of energy spread over this area, and that's a larger area? So that's what actually causes there to be differences in the amount of solar radiation that's received at different latitudes. Okay? So that's the actual cause of that. And it's the same thing like during winter. That's why winter temperatures are less compared to summer temperatures. It has everything to do with the sun, earth geometry, right? And the sun is lower in the sky, and we're getting sunlight at kind of less direct and more at an angle. Okay. Does all that make sense? Clear? So a little bit about the seasons and what causes there to be seasonal variations in temperature. So I already kind of pointed that out, right? So during the winter, the sun is lower in the sky. Its sunlight is not shining directly on the surface. That's what causes there to be kind of a difference. Now, I want to get into a little bit, just so you have some understanding of seasonal variations in the atmosphere. I want to explain a little bit about the seasons. I know I touched on this a little bit at the beginning of the class, but just a little bit more depth here. So you might remember that we revolve around the sun. And by the way, we go around the sun. If you're looking down on the North Pole, we're going around counterclockwise, okay? And if you're looking down on the North Pole, we also spin on our axis counterclockwise, okay? So in case you ever forget about that. It's all going, everything goes everything in the solar system, except, there's a few exceptions, but everything is rotating counterclockwise, okay? So nothing's going against the grain. Venus spins backwards, but that's about the only exception. So. But everything else spins counterclockwise on its axis and also goes around the sun counterclockwise. Now, there's a plane, you can imagine kind of an imaginary plane that is a flat surface that contains our orbit around the sun. And we call that plane the ecliptic plane. Okay? And what's kind of cool is that all the planets in the solar system are orbiting all in that same plane. Okay, so that same ecliptic plane contains the orbits of all of the planets around the sun. Okay? So actually, if you get used to looking at the night sky, you'll notice that actually you can literally see the ecliptic plane in the night sky. And you can see, it kind of depends on the time of year, but you can literally sometimes see the moon and different planets all in an arc in the sky. And that's the ecliptic plane. And it's also the same path that the sun would follow in the sky. Okay? So everything's kind of following the same path, and it's because it's all orbiting in the same ecliptic plane. Okay? Now, we are tilted, of course, 23.5 degrees. Our axis of rotation is tilted 23.5 degrees relative to the ecliptic plane, right? So we've talked about that before, right? Have we, or did I talk about this at the beginning of the class? I thought I did. A little bit, right? A little flavor of it. I'm just making sure I'm not imagining things. So our angle of our tilt is 23.5 degrees, okay? Now, our orbit is actually not a perfect circle. So it's actually something called an ellipse, which is kind of like an oval. You can maybe imagine it as an oval. So, in an oval, in an ellipse, there's times that you're closer to the sun, and there'll be times that you're further away from the sun. Because the circle, you'd be always the same distance. But an ellipse, you're going to be closer and sometimes further away. So the time at which we are closest is called the perihelion. The perihelion, okay? And that actually happens on January 3rd. So we're actually closest to the sun on January 3rd. It's 147 million kilometers. We're furthest away on Independence Day, on July 4th. So if you want to bring that up at your next Independence Day party, over the summer, you could tell everybody that this is actually a sign called the aphelion, and we're actually further away than we ever are. During the course of the year, we're furthest away from the sun, 152 million kilometers, and they'll tell you to get out, I think, probably. Nobody likes to talk about this at parties, I've found. So, what can you do? But yeah, so the aphelion is when you're furthest away from the sun. That happens on July 4th. And then the perihelion is when you're closest. That's January 3rd. So you'll actually notice that during our winter in the northern hemisphere, because remember, the southern hemisphere has everything flipped, right? Their coldest month is July, right? So when we're having nice hot summer, they're having their cold winter, right? But you might notice that actually we're closest to the sun during our winter, like in the middle of our winter. And we're furthest from the sun during our summer. So that's kind of nice because it actually does play a small role in kind of making our winters a little bit not so bad in the northern hemisphere and making our summers not so hot. Because that does play a small difference in climate, right? How far away or how close we are to the sun. Okay, so anyway, that's the aphelion and perihelion. And now there are four very important times during the course of our year. There are four important days, and that corresponds to the four seasons, right? So, I have this picture, but this picture seems to kind of confuse people. So I'm kind of almost thinking about showing this one. But I want to just point something out here, okay? Now notice on this day, do you see how the axis points directly at the sun? Do you see how it's pointing at the sun? It's pointing directly towards the sun. So that day, the northern hemisphere actually gets the longest days, and it gets the most solar radiation, okay? And that day is the summer solstice. And that's when the axis points directly at the sun, okay, in the northern hemisphere. On this day, it's pointing away from the sun. Do you all see that? It's pointing directly away from the sun. So that is our winter solstice, okay? So this picture doesn't show it as well. I kind of want to replace this with something more clear. But the day in which the axis of the Earth's rotation points away from the sun, that is the winter solstice. It happens right around Christmas. So it's about December 23rd, okay? It's not on Christmas, but it's pretty close to Christmas. So December 23rd, okay? That's your winter solstice. The summer solstice is when it's pointing directly at the sun, and that's around June 21st, okay? What's that?
That's a birthday.
Wow, it's June 21st. So those are both very special days in our calendar, right? Because and they're not arbitrary. They're actually all related to Sun-Earth geometry, okay? Now there are times in which the angle at which the sun's rays are coming in are completely perpendicular to our angle of rotation, and those are called the equinoxes. So that an equinox means equal night. So it's the time in which we have perfect 12-hour days, 12-hour nights. So we just passed the vernal equinox, the spring equinox. So the spring equinox is on March 23rd? Yeah. Oh, up here, March 21st, sorry. So March 21st. So right now, the length of our days should be pretty close to 7 hours. It's going to be a little bit over 7 hours because we've already passed the vernal equinox. But so maybe it's 12 hours and 15 minutes right now or something like that. Okay? And then we have the autumnal equinox, September 23rd. So if you look at the diagram, number 25, right? A lot of people just copy what they see up here. And you might notice that I think it's actually backwards. In fact, it is backwards. Do you all see that? So be very, very careful on number 25 when we have to fill this out. Don't look at this diagram. Look at the geometry you see. So when the northern hemisphere axis is pointing towards the sun, that's the summer solstice, right? When it's pointing directly away from the sun, that's the winter solstice. And then you can easily figure out the equinoxes because, right, what's between summer and winter? Yeah, fall. And then what's between winter and summer? Spring. And the arrows, do you see on how number 25 is showing you the arrows to show rotation, right? So it's going counterclockwise like it should. Okay, so does that all make sense? Did you get that all filled out? So we have those 4 special days that conform to the 4 seasons that we go through, right? Okay, so during the summer solstice, the sun is actually directly overhead the Tropic of Cancer, 23.5 degrees north. So on the summer solstice, the sun is directly overhead that point, the Tropic of Cancer. But it will not go past the Tropic of Cancer. Right? So if you live north of 23.5 degrees north, you will never have the sun directly overhead. So here in South Texas, does anybody know our latitude about?
25.
Yeah, it's around 25, 27. So we are north of the tropics, right? So are we ever going to see the sun directly 90 degrees over our head? No, it'll never happen, right? If you ever see the sun directly 90 degrees over your head to the point that you have no shadow, just coming right straight down, there's a huge problem. I don't know what, but it would be a really big problem. It should not be that way. So it's 23.5 degrees. Is the tropics, right? And that's why we have the tropics, by the way. It's not like somebody just said, hey, it's hot between here and here, let's make it the tropics, right? It has everything to do with Earth-Sun geometry. So 23.5 degrees north. And then during the winter solstice, where do you think the sun is? Directly overhead which line of latitude? During the winter solstice. 23 south. 23.5 degrees south, which is the Tropic of Capricorn. Okay. And then during the equinox, where is the sun directly overhead at? Because imagine during the equinox, you would straighten this all out and it would be directly overhead at the equator. Okay. So that means over the course of a year, if you live anywhere in the tropics, there's actually going to be 2 points during the year in which the sun is directly 90 degrees overhead. Unless you live on the Tropic of Capricorn or Tropic of Cancer, then there will only be 1 point, which is directly overhead. But if you live in between those lines, like if you live at the equator, it'll be directly overhead during 2 points during the course of a year. But here at mid-latitudes, where we don't have the sun directly overhead ever, that doesn't happen. Now you might notice that within the polar areas, right, within the high latitudes, you probably heard of like the polar, the Arctic and Antarctic circles, right? That's actually at 66.5 degrees north and 66.5 degrees south. And those numbers weren't, again, it wasn't like just randomly chosen. It's that 66.5 is equal to 90 minus 23.5. So within the Arctic and Antarctic circles, you literally get at least 1 day in which the sun does not come up during the winter. And during the summer, you get at least 1 day where the sun does not go down all the way. Okay. Did I show you videos of that at all? I think I may have showed you, because I talked about this again at the beginning, so I think I showed you a video about it. But it is crazy. And then if you're at the North Pole or the South Pole, it's the most extreme, right? The sun will not come up during the winter at all. You will not have sunlight during the entire winter. And then during the summer, during the entire summer at the North Pole, the sun will never go down for a whole 6 months, right? So it's crazy. But that's why nobody lives there, right? So, okay. So did I hit everything that's on number 16? I think I did, right? So there's the. So this is in 77 degrees north. So that's within the Arctic Circle, right? Because it's above 66.5 degrees north. And this would be during what season, do you think? Or I could just ask this. You know that it's not during the winter, right? Because this is the midnight sun. So it's got to be sometime during the summer or the spring. So it gets very, very close to the horizon, but does not actually go down all the way, right? And you know I always find this very crazy, but this is true. At the North Pole on the summer solstice, the North Pole on the summer solstice gets the most solar radiation than any place on Earth, even the equator. Even on the hottest day of the equator, it doesn't get as much solar radiation as the North Pole on the summer solstice day. And that's because it gets 24 hours of sunlight on that day, right? So anyway, there's the midnight sun. Again, I showed it again. Okay? So we finished everything on lecture assignment number 16, right? Okay, so now we're going to move on to atmospheric circulation number 2, lecture assignment number 17, okay? So now that I've kind of given you a whole bunch of background on pressure and temperatures and how these things vary over the surface of the Earth, we're actually going to get into the actual global circulation patterns that we see on Earth, okay? So this is kind of more of the meat and potatoes of what you need to learn here so that you can understand ocean circulation next week, Okay, because after this, after we do atmospheric circulation, we're going to get into currents and ocean circulation, and it's not going to make any sense if you don't understand these patterns of circulation in the atmosphere. Okay, so now we're actually going to talk about how these cells, we actually have convective cells, 3 major convective cells that go over the surface of the Earth that you need to understand here. So we're going to get into that now. So global air circulation, air pressure, and wind. That's what we're going to start right now. So this is number 17 here in your lecture assignment packets. So, of course, as you know, number 1, it says what happens to air pressure as you move up through the atmosphere? Well, you're pros at this now, so you know this already, right? So what happens to air pressure? Decreases, right? It drops off. So does air density. It all drops off as you go up into the atmosphere. Now, a little bit about how we measure air pressure. Because air pressure is kind of it's a little bit annoying because we use a lot of different units. There's a lot of different units employed to measure air pressure, okay? So some of those units are, are bars. Probably, has anyone ever heard of a bar? Ever heard of that term for measuring air pressure? A bar? So a bar is defined literally as one unit of standard air pressure at sea level. Okay, so right now, you're sitting here right now, the amount of air pressure that you're feeling is about 1 bar. Okay? So you're feeling about 1 bar of air pressure. Did you know that you're under pressure? Yeah, you're actually under a lot of pressure. There's actually a lot, actually. You actually, this is kind of, I always kind of think about this crazy. You actually have every inch of your body experiences 15 pounds of pressure. Did you know that? You got 15 pounds sitting on every single inch of your body. You have 15 pounds. So it's kind of a lot, if you think about it. You think, wow, look at all the inches of my body. It's a lot of pounds sitting on top of me, right? So what is that weight? Like, why do you feel 15 pounds for every inch of your body? 15 pounds per square inch. Where is that weight coming from? Gravity, but it's something that's sitting on top of you. It's the gravitational force of something that's sitting on top of you right now. The air, right? Because you have like 100 kilometers of air sitting on top of you right now. Okay? Just like you feel like you probably dove down probably some of you swim, right? You maybe dove down to the bottom of like the deep part of the pool. Has anyone ever done that before? You ever feel like your ears really, you get that, you feel that pressure. Even only 10 feet of water, you can really feel a lot of pressure, right? So it's the same thing. You have this big column of air sitting on top of you. That's what's causing that pressure. So you feel some air pressure at a sea level, okay? And the air pressure is highest right at sea level. So it's 1 bar. Another way that this is commonly expressed is inches of mercury. If you really want to understand why they use mercury and where that inches of mercury is, I'd be happy to explain it to you, but there's no need to understand that right now. But just know that we also measure pressure in inches of mercury. This is a really common way of seeing, and probably if you listen to the weather report, like here in Corpus Christi, they're going to give it to you in inches of mercury. They're going to give you the pressure in inches of mercury. Bars is more of like a metric system thing. Okay, so you have inches of mercury. Now, the metric system, of course, 29.92 inches of mercury is what we often use in America. But if you use the metric system, that's expressed sometimes in millimeters instead, so it's 760 millimeters of mercury. And then, of course, there's 1 bar, okay? And then 1 bar, you can also, sometimes they break that up into millibars. So how many millibars are in 1 bar? You should know that from metric system prefixes. How many millibars in 1 bar? Millibar? How about this? How many millimeters are there in a meter? Millimeters in a meter. You forget? Do you remember, Kaya? 1,000, right? So there's 1,000 millibars in a bar, just like there's 1,000 millimeters in a meter. Okay. All right, so you are feeling Oh, I'm sorry, there's a mistake. E. It says pounds per square foot. I'm sorry, it's square inch. Square inch. So the number of pounds per square inch, that's another way of expressing pressure. You probably know that from your car. Do you ever measure the pressure in your car? No? Okay. No? Okay, I guess I'm the only one. But, you know, the pressure in your tires is usually something like, I don't know, it should be something like, 30 PSI. PSI is pounds per square inch. So right now, on top of you, you should be feeling 15 PSI, right? 15 PSI, 15 pounds per square inch. So if the pressure inside your tire is only 15 PSI, it means your tire's flat. Sorry. So don't think you have any air in your tire if you have 15 PSI, because it's just normal atmospheric pressure. Okay. And yet another way, again, metric system version of PSI is kilograms per cubic centimeter. Okay. And there's actually 1 kilogram per cubic centimeter. Okay. So that's another way of expressing it. Have you all ever been on an airplane and maybe you have like an empty bottle of water, or maybe like sometimes you bring in like a bag of Cheetos or something, and then you start going up on the airplane, and then a bag of Cheetos never lasts that long for me, but if you did have one, and then you go up in the airplane, and then by the time you get up in the atmosphere, way up high, the bag of Cheetos is about to blow up. Has anyone ever seen that before? No? Okay. I'm using all these examples of things that nobody knows. So it's all right. How about this? Has anyone ever seen this before? You have a bottle of water, maybe you're up in the mountains, and then by the time, or maybe you're up in an airplane, you have a bottle of water, and then you land, and then your bottle looks like that's all scrunched up. So you're seeing the change in air pressure with altitude. So that's what that's supposed to demonstrate. Okay, so we measure these, or I shouldn't say we measure, but we plot out these differences in air pressure over the surface of the Earth in things called isobars. So isobars are like contour lines. In fact, they are not like contour lines, they are contour lines. They're a little bit like topographic lines, but they're just lines of equal pressure. So this is a way of just kind of mapping out where high pressure systems and low pressure systems are. So where the pressure might be particularly high one day, and where the pressure might be particularly low. Now the reason that you get low pressure systems and high pressure systems, has anyone ever heard of stuff like that? Like, have you ever listened to the weather report on the radio or anything like that? I don't know if any of you ever listen to the radio, but does anybody listen to the radio anymore?
Not for news.
Yeah, not for news, yeah. But I don't know, sometimes, I guess it's kind of an old-fashioned thing now to do, is everybody listen to the radio to get the weather report. But sometimes they will talk about, like, there's a weather, or sometimes like on TV, the weather, if you're listening to the weatherman, they'll talk about like a high-pressure system coming in or a low-pressure system coming in. Have you heard that before? Okay, so those high-pressure systems and low-pressure systems, the cause of those things, the reason that this over here is low pressure and this over here is high pressure, it's from the air either ascending or descending. So in places where the air is descending, it's coming down, blowing down, it creates high pressure. And the places where the air is lifting up, it's low pressure. Does that make some sense? You could imagine if there's vertical movement to the air is lifting up, that would kind of make, you could maybe imagine there'd be relatively lower pressure. Okay. Places where the air is coming down, it's going to be high pressure. Okay. So that's actually literally what you're looking at right here is a map of air, like the vertical movement of the air. High pressure is when the air is coming down, low pressure when the air is rising up. So what happens when air rises? It cools. Yeah, and then it hits the blah blah point. Dew point, hits the dew point, and then it rains, right? So what kind of weather do you think these people over here are having with the low pressure system? Yeah, like overcast and rainy kind of weather. Okay? And then here in the high pressure system, what happens when air comes down and descends? What happens to the temperature of that air as it descends and comes down and compresses? It gets hotter. So what kind What kind of pressure do you, or what kind of weather do you think they're having over here? They're having like hot, and this is, by the way, so these are like days when we get a high pressure system coming here in Corpus. Actually, we've kind of been having days like this where it's really crystal clear outside. There's no clouds, and it's hot. That's high pressure. Low pressure is when you start seeing the clouds building up, and it's, you know, maybe it rains and blah 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 blah. So that's low pressure. Okay. All right. So taking a look at this, here we got the high pressure. We have the low pressure. So let me ask you something. If you were just going to guess wind, you all know about wind here in Corpus, right? So we have a very windy city. If you were going to guess, here's the high pressure, here's the low pressure. What would you guess is the wind direction here? How would you draw, what would you guess would be the wind direction? Do you think the air would just be squeezed right out, go right over there, going from that high pressure system to straight over to the low pressure system? No, you don't think so? Why don't you think so? Is it too easy? You know it has to be more complicated than that, right?
Because wind doesn't just go straight.
Yeah, that's true. It doesn't just go straight. So maybe if you were to look at this and not knowing anything, you might assume that wind would just go straight from the high pressure to the low pressure, right? Because you know how things are. If you squeeze, right, like this guy, you know, it goes from the high pressure area inside the bottle to the low pressure area outside. So you might assume it would go like that. But it actually does something really freaky. The wind direction is actually shown by the arrows. So do you see those red arrows? So what are the red arrows doing? Yeah, they don't cross the beams. If you've ever seen Ghostbusters, it's just like that. They don't cross the beams. They don't. I had a weird dream this morning. I dreamed I was. Has anyone ever seen the 1985 Ghostbusters #1? I dreamed I was in that movie. It was one of the Ghostbusters, and the Marshmallow Man, and everything. And I had to knock. I had to cross the beams. That was the only way to destroy him. It was weird. So anyway, that's why I'm thinking of Ghostbusters right now. That's why it doesn't cross the beams. But anyway, do you know what I'm talking about? You've seen that movie? I hope. I don't know what the new one's like, if they cross the beams or not. But do they cross the beams in the new one? I don't know. It doesn't matter. But the wind doesn't cross the contour lines. It goes. So do you notice that? It's kind of crazy because you would expect the wind to just go straight cross all the contour lines, and go straight from the high pressure to low pressure, but it doesn't. Instead, it goes along with the contour lines. Okay? So that's weird. You should kind of look at that and be like, that's weird. That's really weird. It shouldn't do that. Okay. So this high pressure to low pressure is called the pressure gradient force. Pressure gradient force. Pressure gradient force. So that's the actual force. It's the pressure force that is moving the air. But the air does not actually follow the pressure gradient force. Do you all see that? In fact, the air usually travels perpendicular to the pressure gradient force. Do you see that? All right, so this is very important, guys. I want you all to pay attention now and just look at this and focus on this, because this is going to comes up a lot when we talk about ocean circulation, okay? So that's the force. The pressure gradient force is moving the air, right? That's what's the force driving the air. But the air moves to the right of the pressure gradient force everywhere here. Okay? So you all see that, right? So why doesn't it go with the pressure gradient force? Why does it go and divert perpendicular to the right? It's a perpendicular angle. So why does it go to the right? The reason, does anybody have a guess? Does anyone ever seen this before? Okay, so the reason is that your friend, the Coriolis force, who is never going away for the rest of this class. So get to know Coriolis force, okay? So the reason is Coriolis force. So I'm about to explain what that is, okay? So number 3, you got that. What's an isobar? It's a line of equal. It's a line that shows equal pressure, okay? Number 4, what is the wind direction relative to the isobars? It doesn't cross the bars. It's parallel to the bars. Number 5, what is the pressure gradient force? It's the force that drives wind. That arises from differences in pressure. What is wind direction relative to the pressure gradient force? It's perpendicular, 90-degree angle. And in the northern hemisphere, it's 90 degrees to the right. In the southern hemisphere, it's 90 degrees to the left. Okay? So we all got that? Does that all make sense? Oh, number 7, I haven't talked about that yet. Do you see how some places the isobars are close together, some places they're farther apart? So maybe like right here, they're pretty far apart. You see that? So the isobar spacing is like right here. Look how far away the isobars are. And then right here, isobars are pretty close. So you all see that, right? All right, so that's actually what controls wind speed. Okay, so the closer the isobars are together, the higher the wind speed you're going to get. So you would expect really high winds right here and very low winds out right here. So here in Corpus Christi, there's usually a pretty high, almost year-round, a pretty high pressure gradient force, right? For whatever reason. Because we almost always have pretty high winds.
The isobars never move.
Oh, they move. Oh, they move all the time. They're always moving. Because what you'll see is that these pressure systems will actually migrate to the left or to the right, or they'll go all over the place. They're constantly moving. So that's a great question. So this is really just a moment snapshot in time. All right, so so why doesn't wind follow, number 8, why doesn't the wind follow the pressure gradient force in direction? Because of the Coriolis force. It's offset, it's diverted, I can say, by the Coriolis force. And now, what is the Coriolis force? That's what we need to figure out. Because it's going to, like I said, we're going to see this doesn't only affect stuff in the atmosphere, it affects the water as well. Water is actually directed by the Coriolis force. The currents in the ocean are directed by this force as well. So we really need to have a very good understanding of Coriolis force. So, if you're distracted right now with something, you gotta buckle down and pay attention, because this isn't going to go away. It's not something you can ignore, the Coriolis force. Okay, so there's pressure gradient force. We already talked about all this. Okay, here's Coriolis force. All right, there's a lot of. I'm going to try to show a lot of GIFs to explain this, because it's kind of hard to understand. But the Coriolis force is we can call it a fictive force. It means it's not a real force per se, but it arises from the rotation of the Earth. And remember that Earth is rotating. If you're looking down on the northern hemisphere, it's going counterclockwise, right? So like that actually. So it's the Coriolis force is the deflection of any moving fluid over the surface of the Earth due to the rotation of the Earth. It's 0 at the equator, where the Earth spins fastest, and the magnitude of the Coriolis force, it increases as you go towards the poles. So in the North Pole, you're going to get a lot of Coriolis force. Near the equator, you're going to get no Coriolis force. So I'm going to try to explain why this happens, okay? So please listen carefully. Now imagine our Earth here is spinning, right? At the equator, you're spinning very fast, okay? Because the radius of the Earth is greatest at the equator, right? Imagine if, maybe you could even imagine like a record player. Oh man, you all know what I mean, a record player. Spinning around. Okay, if you're standing at the outside of a record, like imagine you're standing at the very edge of the record player, you're spinning really fast around, you're actually moving pretty fast. But if you were standing right at the center of the record player, you'd just be kind of turning around like this, right? But you wouldn't actually be moving fast at all. You'd be turning, but you wouldn't be moving, right? So when you're at the equator, you're moving really fast. You're actually moving like close to 1,000 miles an hour as the Earth spins. Okay, I know you don't feel it, but you are moving about 1,000 miles an hour. Now here in Texas, you're at about 26 degrees north, you're maybe spinning like 800 miles an hour. And as you go towards the North Pole, that goes all the way to 0, okay? Now imagine this. So let's say you're right here, okay? And you're a mass of air, and you're trying to move, you want to move north. All you want to do is go north, okay? So you start moving to the north. But because the Earth is sort of, you think you start off, you're moving very fast to the right. Or I guess actually no, you'd be going actually to this direction, to the left. But as you move north, the Earth is not spinning so fast underneath you. So you retain that rotational momentum from where you started off. So what's going to happen is you're going to veer to the right. And no matter what you do, you're always going to veer to the right. If you try to go south, what's going to happen is you're going to have the smaller rotational momentum from this place you started off in the south, and you're going to again veer to the right. So no matter what you do, whenever you're trying to move over the surface of the Earth, and if you're a fluid, like you're the air or the sea, you're going to veer to the right in the northern hemisphere. The opposite happens in the southern hemisphere. You're going to veer to the left. Okay? Maybe another way to imagine this is like you're trying to... I put some GIFs up here to kind of maybe try to hopefully explain this better. So this guy's trying to move to the south, but the Earth is rotating under it, right? And so you see that there's a deflection from the intended path. This is, by the way, the next thing I'm going to show you is, I think it's the best way to visualize this. Okay, I'm going to show you something in just a minute. It's a merry-go-round. And people are going to be sitting on the I don't know if they even have merry-go-rounds anymore. I had them when I was a kid. I guess they're too dangerous. People get
They have the little ones up here.
Well, that's good. Thank goodness. But, you can sit on a merry-go-round. If everybody sits at a merry-go-round and try to throw a ball while you're on the merry-go-round and watch what happens. Has anyone actually ever tried to do this? Watch what happens. So they're going to try to throw a ball. So see how they're trying to throw it directly across to the other person, but it keeps veering off in the wrong direction. Okay? You see that? It's trying to throw it straight across, but it gets veered off to the other direction. So this is a perfect depiction of the Coriolis force. Now, is the ball veering off to the left or to the right? To the left. So here's a question for you. If it's veering off to the left, if we look down, should they be spinning clockwise or counterclockwise? I guess you'll see it in a minute. Notice how they're going clockwise? That's opposite of what the Earth does. It goes counterclockwise, looking down on it, right? So that's why you see the thing veering off to the left here, but on Earth it'll veer off to the right. Okay? So this is, I think, the best depiction of how to understand the Coriolis force. This happens not only with the air in the atmosphere, but it happens with the ocean water as well. Okay? Coriolis force will affect both these things. And in the ocean, it gets even more complicated than this, so get ready. So that's why I'm saying you got to know Coriolis force now, because it gets even more complicated when we talk about Coriolis force in the ocean water. Okay? So there you have it. Okay, so we got Coriolis force. What time is it? 12:07. Oh, wow, it's 12:07. Okay. All right. In the northern hemisphere, Coriolis force deflects fluid to the right. Yeah. In the southern hemisphere, it deflects it to the
Left.
Okay. In the northern hemispheres. Oh yeah. Let's take a look at this. So remember that with a low pressure system, you know, wind and water, it's always going to go fluid. It's always going to go from high pressure to low pressure. Okay. So what's going to happen because of Coriolis forces? You're going to get these spirals. You know, these cyclones. That's why when you see a hurricane, right? The hurricane's turning counterclockwise, right? You better hope it's going counterclockwise. So what happens is with a low pressure system, you get these spirals of air inward into the low pressure system that are going to be going counterclockwise, right? And the reason is here's the pressure gradient force. It's into the low pressure system, right? It's into it. The pressure gradient force is going into the low pressure system. Y'all follow? Okay? And it wants to go in, but it gets deflected to the right, deflected to the right, deflected to the right. So that's what creates you see what's happening here? That's what creates these inward counterclockwise spirals around low pressure systems. So when you see a hurricane coming towards Corpus, you'll notice it's always spinning counterclockwise and the air is spinning inward at inward spiral counterclockwise because hurricanes are giant low pressure systems, very powerful low pressure systems. Okay? The opposite in the northern hemisphere, or in the case of high pressure, the air is being pushed outward, so it's an outward spiral of air. And again, it's always going to be moving to the right, deflected to the right. So you're going to see that things are going to be going clockwise. So we call these, by the way, a term we have for these are cyclones and anticyclones. Low pressure systems are called cyclones, anticyclones are high pressure systems, okay? So you probably heard that term of a cyclone before, right? And you probably think of it as a storm. And it is, I mean, a low pressure system usually is a storm. So a very powerful cyclone, a very powerful low pressure system could generate, you know, a storm. So that's why sometimes you probably heard that term. One thing I really like is this website where you can get real time, you can see what the global wind direction is anywhere. And it's kind of cool visualization. This isn't what I wanted though. I didn't want this. This is not. So at any given time, you can see wind directions on this map. It's all visualized. Okay, so let's look here. Notice that when you are close to, so you see America right here, right? Y'all see that? Let me turn another light off so you can visualize this better. Now near the equator, do you see any spirales? No spirales, right? Why is there no little spirals near the equator? There's no, what? Coriolis force, right? No Coriolis force, so you see there's no spirally guys down here. When you get up into the higher latitudes, you notice you start seeing spirals. So this spiral right here, is that going clockwise or counterclockwise? Counterclockwise. So that means it is a what kind of pressure system? Low pressure system, right? So you all see that? So that's a low pressure system right there. Now if we go to look at the south, look how many spirals there are, right? This is, you see that's Antarctica right there? So I'm looking at Antarctica. This is the Southern Sea. You can see there's lots of, now what direction is this all moving in here? Counterclockwise or clockwise? Clockwise. So in the southern hemisphere, these clockwise rotations, what kind of pressure systems are those then?
No.
They're going to be low pressure. Because you go clockwise for a low pressure in the southern hemisphere. Remember, everything's reversed for the southern hemisphere. So just remember, everything's, usually the way I memorize this is I just memorize everything for the north, and then I flip it in my mind for the questions for the south. So the deflection, Coriolis deflection in the southern hemisphere is going to be to the left, and it's going to create clockwise spirals around low pressure systems and counterclockwise spirals around high pressure systems in the south, in the southern hemisphere. Okay, so, but you can see at the equator, there's no big spirals going on right on the equator. You have to get a little bit, oh, that actually looks like a tropical storm or something right there, doesn't it? Kind of looks like it's getting something like that. So it's going, but that actually, now I look at it, that's a high pressure system. So that's not a tropical storm, it's a high pressure system. Okay, so anyway, I hope that gives you some visualization of these things. No, that's not it. All right, so let's see. So we got up to number 11. We already talked about number 12. Descending air creates high pressure systems. Ascending air creates the low pressure systems. So what is creating the low and the highs that you see over the map? It's from the air. It's either moving up or it's moving down. If it's moving up, it's creating the low pressure system, and that's why you usually see like stormy weather on those days, because the air is moving up, it'll cool down, it'll hit the dew point, it'll precipitate. Okay. All right, now the global circulation belts, it's a can of worms, and we're already out of time, so we're just still playing catch up, unfortunately. Yes, Francis?
Can you read off the other?
Sure. So in the northern hemisphere, wind spiral, it should really, sorry, that's a typo. Wind spiral, I should say winds, spiral inward, and counterclockwise due to low pressure systems. And they spin outward. Oh, I'm sorry. And they spin, low pressure system is still going to, so yeah, low pressure systems, they're always going to spin inward. They're never going to spiral or spin outward. They always spin inward, right? Because the air is always going from high pressure to low pressure. So it's always going to spiral or spin inward, and it's going to be deflected to the right, so you don't need to know that, but it's going to be counterclockwise in the north, and it's going to be counterclockwise in the south. I'm doing a horrible job, aren't I? I'm a bad professor. Counterclockwise in the north, clockwise in the south. I have to fix this question, it's too confusing. I'm sorry. Even I'm getting myself all mixed up.
So it's clockwise in the south, correct?
It is clockwise in the south, correct. Yes. Counterclockwise in the north. Oh, yeah, hi, Hayden. Yeah.
We leave 15 and take
Please leave number 15, and if you want to leave 16 as well, that's okay. But if you want to continue working on 16, that's all right as well. But do leave number 15 today. Do leave number 15, okay? And I will see you on Wednesday. So have a good couple days.